All right, how are we going to graph our inverse trig functions? And if all we have to graph is one inverse trig function, we pretty much draw the same graph every single time, but just adjust the scale is easier to do it that way. So if you've got your math aid, piece of cake, you just put your math aid down, draw it, and then put it in the right scale. But what is that scale? How do we work out the domain and range of our inverse trig? So here's this one, 5 inverse sine x on 3. Now the way I work out the domain is I say, well look, normally the inverse sine, and we just have inverse sine x, and I know x goes between minus 1 and 1. So now x on 3 is going in between minus 1 and 1. Multiplied by 3, we get our domain. So x for this particular curve is going between minus 3 and 3. I can do a similar thing with the range, but I need to group the number with the y, of course, because y refers to range. So normally, y goes between minus pi on 2 and pi on 2. So for this one, it'll be y on 5. Goes between that. Multiplied by 5, and we get our range, minus 5 pi on 2 to 5 pi on 2. So in order to now draw that graph up, as I say, I could draw exactly the same as I did before, but now I just mark the endpoints as minus 3 and 3 on the x-axis, and on the y-axis I'll label them minus 5 pi on 2 and 5 pi on 2. Inverse tan of the square root of 3 minus x squared. This actually turns to be something quite interesting. The domain. Well, normally for an inverse tan graph, the domain is all real x. However, this time I'm substituting into the square root. And so just like when we looked at square root graphs, we can't find the square root of a negative number, so we have that restriction on the domain. And so for this one, x is in between minus root 3 and root 3. Now, because I have restricted the domain, that is going to affect the output, the range. So let's substitute in, and we can see that at root 3 we get 0. At minus root 3 we also get 0. It is an even function, you'll notice, because of the x squared. So a good idea to check the midpoint then as well. And that should cover our range. At the midpoint, which is of course 0, we get pi on 3. So the range, it looks like, goes between 0 and pi on 3. Now what does it actually look like, eh? Voila. So there it is, the inverse tan of root 3 minus x squared. Looks a bit like the semicircle, but of course it's not, because if you look at the scale of it, I mean that's minus root 3 to root 3, but on the y-axis it's going to pi on 3. Oh, so maybe more like an ellipse, I suppose, then, isn't it? Because it has a different radius. The inverse sine of sine x. So domain. We are actually substituting our x value into the sine function. Now, we can sub anything into the sine function, that's fine. However, then that answer, so the answers from sine x, are being substituted into the inverse sine function. So basically what we're saying is, normally inverse sine of x we have, and x is in between minus 1 and 1. Now we're saying, hey, actually it's sine x we're substituting into inverse sine. So we want to know when is sine x in between minus 1 and 1. Now if you think of your sine graph, when is the sine graph in between minus 1 and 1? Yeah, it always is. So the domain will actually be all real x for this particular one. But now the output. Well, the output then, if I can sub any value of x in, and I'm going to get the complete domain, because sine x goes from minus 1 to 1, so I know I'm substituting the complete domain in, it also means the range will now be unaltered, because it is possible to sub in every value of the normal inverse sine graph. What will it look like, though? Well, it's obviously going to look something like the line y equals x, because inverse sine and sine would cancel out. But it's not going to be the complete line y equals x, because we said the domain was in between minus 1 and 1. And we said the range was in between minus pi on 2 and pi on 2. Now, actually, is that the right graph? Domain we said is in between, oh no, sorry, domain is all real x. Phew, I thought I had the wrong graph there for a sec. But the range is only going up from minus pi on 2 to pi on 2. So we've just got that section of y equals x. But the domain is all real x, so it does keep going. It just can't keep going like the line y equals x. So we could plot some more points. If I picked, say, pi as another point, well, if I was to sub that in, the sine of pi is... Good, don't all rush me there. Okay, 0, and the inverse sine of 0 is... So I know at pi, I'm going to be back at the x-axis. Same at minus pi. And I can pick other points. What ends up happening is we get this like zigzag. It'll be zigzagging all the way along the axis. So that's the inverse sine of sine x. Swap it around the other way, something different happens. So it's now the sine of the inverse sine of x. So this time domain is only going to be minus 1 to 1. Because the first thing we're substituting into is the inverse sine function. And that has domain of minus 1 to 1. So I can't substitute in anything bigger than 1 or smaller than minus 1. The range, oh well, if I've got a restricted domain, let's test the endpoints. Let's see what happens. So when x equals 1, we get the sine of the inverse sine of 1. It does turn out to be 1. At minus 1, it turns out to be minus 1. In the middle, let's have a look at that as well. Yeah, that's 0. So it does appear that our range is also going to be between minus 1 and 1. I guess that makes sense because, again, you would expect it to be based on the y equals x curve. So this one is just the piece of the line y equals x that goes from minus 1 to 1. So unlike the other one, it doesn't then zigzag all the way along. It's just that one little piece of the graph y equals x. Okay. 1C.